The next speaker is Jong-Wan Lee, who will talk us about parity learning in two-color and two-flavor gauge theory at high temperature.
Okay, thank you. In this talk, I would like to present my recent work on the metal spectrum of SU2 two-flavor theory at high temperature in collaboration with Jong-Wan and Marucho PI. Okay, so as you heard in previous talks, the SU2 gauge theory is also interesting as in the model building of the beyond the standard model. So, for example, in previous talk, the SU2 gauge theory with two flavor in fermions in the fundamental representation can be considered kind of as a minimal model for different color, compact Higgs or dark matter. But there are a couple more motivations why we care about SU2 gauge theory. So first of all, it shares some non-perturbative properties with QCD, such as confinement and charismatic breaking. And also, the theory with even number of fundamental fermions are free from sign problem, which is the main obstacles in finite density calculation of QCD. So recently we started to working on this SU2 gauge theory with two fundamental fermions at finite temperature calculation. So by implementing the anti-Taylor boundary condition in temporal direction, the temperature is given by inverse of the n tau times A. A is a lattice spacing. So there are two ways to change the temperature. The first way is fix n tau and changing the lattice spacing by changing the beta values and the action. The other way is the fixing the lattice spacing and change the n tau. But in this case, because at high temperature, the n tau is very, we have limited number of n tau. So in our calculation, we introduced anisotropic lattice to get better the resolution in temporal direction. Okay, so in previous talk, you already heard about the theory. So this is a Lagrangian, and the in this talk, in our calculation, we focus on the symmetry. I mean, the global symmetry SU4 broken out SB4, and because of the existence of the chiral condensate with finite mass, the mass also explicitly breaking this symmetry. Then we have the 5 Folderson bosons and 3 usual pseudo-scalar mesons and 2 dipole baryons. With just these mass terms, we cannot distinguish these the pseudo-scalar mesons and dipole baryons. So in the real calculation, our two-point Fourier function are degenerate. Okay, our observers are isobacter mesons. The operator looks like this, and different with different types of gamma structures. Okay, before I go on details of our anisotropic lattice, I want to mention there are a few applications of this anisotropic lattice. So basically, any lattice calculations which requires a fine temporal lattice spacing while keeping the moderate size of the spatial lattice, we can use these techniques. So comparing to the isotropic lattice with very fine lattice spacing, this is much cheaper. Okay, so first example is the Hepcock simulation where the cutoff effects with the Hepcock mass. So the mass is very heavy, then we have severe the errors from systematic errors from cutoff effects. So in this case, we can implement this anisotropic lattice to reduce these systematic errors. The other example is the spectroscopy of excited state or glucose. So in this case, you know, on the Euclidean formulation, we extract the mass from the two-point correlation, and when the mass of hadrons or glucose are too heavy, then we don't have the lattice data points to extract the mass from the correlators. before we get very large noisy. So in this case, we can also use this technique. And final example is the finite temperature calculation. You already heard many times on the first day of this conference. We can construct this vector function from the lattice Euclidean temporal correlators. So in this case, if we have very fine resolution in the temporal direction, we might achieve very good the understanding of this spectral function. Okay, so this is we use the standard Wilson action, but we treat the temporal direction and spatial direction separately. So we have additional two Bayer parameters. One is the Bayer gauge anisotropy in the gauge action, and the other one is Bayer Fermion anisotropy in Fermion action. Okay, so in the existence of the interaction, we cannot guarantee these Bayer parameters are same. And so we have to tune these parameters where the renormalized gauge and Fermion anisotropy are the same for given point mass. And throughout this work, we fix the lattice spacing where beta equals 2.0. Okay, so how do we calculate the gauge anisotropy from the renormalized gauge anisotropy? So in this case, we use the so-called Clausen's method. The basic idea is that we calculate the ratios of these Wilson loops in t and x direction, and also we calculate the same type of Wilson loop in x and y direction. Then in the asymptotic region, this ratio is basically the potential. So we assume in the asymptotic region, we expect these ratios will be same up to this gauge anisotropy. In practical, we calculate the difference between these two ratios and minimize this function L. Okay, but the problem is that for small size of Wilson loop, we are suffer from short range lattice artifacts. On the other hand, for large Wilson loops, we have very huge noise. So our strategy is to fix the maximum value of x times y before we encounter the very large noise, then scanning this minimum value of x times y from below. Then we expect this xz approaches to the asymptotic value. So here is an example of the calculation, xz inverse versus minimum x times y. And this purple triangle is for this calculation including all types of Wilson loop. And these blue circles, for these blue circles, we exclude the y equals 1, which make very large the small lattice artifact. So for these blue data points, we might say this xz is asymptotically like this value, but it is not clear from this data where we truncate the minimum x times y. So as far as I know, there is one new method using gradient flow by these guys, but in our calculation, we simply extend the Clausen's method, including the non-planar Wilson loops. So the idea is that we use the information on the z direction as well. So instead of this x, one of the side of the Wilson loop, we introduce the in xz plane the shortest path from here to there. So in this way, we can we can have much more data points for small value of minimum x times y. Instead, now we have r times y, where r is the distance between 2 points. Okay, so this is the result. Comparing the previous plots, we add these red squares and this green dynamo. So as you can see, the XZ is clearly approaches to some asymptotic value. So by balancing the systematic errors from small Wilson loop and the large statistical errors from large Wilson loop, we decide to use the minimum R times Y equals 6 to extract XZ. Okay, what about the Fermion sector? So in the Fermion for the calculation of Fermion anisotropy, we just use the simple distribution relation for mesons. So in our case, we use the pseudo-scalar bosons mesons for this calculation. So for non-zero momentum, the E square equals m square plus p square divided by xf square. So we measure this energy in terms of the momentum, and we in our calculation we use these 4 different momentum for the feeding. And this is a typical effective mass plot for non-zero momentum. And this blue blue lines are the constant feed to the effective mass in the asymptotic region. So from this calculation, we extract the energy in terms of the momentum square, basically. Then, as I said, we use these 4 different momentum, and for a consistent check, we also calculate the higher momentum, the energy for higher momentum, and we found that they are consistent. And we found, for this example, XF was 6.36. We also have another consistent check for XF from the distribution relation for vector mesons. So for vector meson, we also did the same calculation, and the value is the XF equals 6.41, which is consistent with the previous calculation. Okay, so we are ready to perform the tuning. So we use these 13 ensembles on 128 times 12 cubic lattice and beta 2.0, and this is the simulation details. We just modify the hierarchy code, which is the HMC. We're using HMC algorithm. Okay, so from here I'm going to show you a bunch of plots, but there is basically our answer for renormalized parameters for given the range of Bell parameters are linear. Okay, so this is for the mass. We use the pi mass square, linear in, we expect linear in XZ naught, XF naught, and M naught. So yeah, we found pretty linear data points, and the fit works well. And for the XZ, we also find very nice linear behaviors. But one thing I want to comment is that okay. So here, this XZ and XF has very mild dependence on the mass. So basically, if you tune the parameters for some target value, the XZ and XF doesn't change much. Okay, so from the feeding, we found these numbers for the coefficient in this linear answer, and we need to impose the renormalized condition. So for given the quantum mass or pi mass square, we need to tune the XZ. We have to impose the condition XZ equals XF equals Xi. So from this condition, we can extract the Bell parameters, which can be used for the real simulation. Okay, so our target value is Xi equals 6.3, and the pi mass is square is 0.005. So in this mass, pi mass square versus Bell mass plot, our target values are here. Okay, so we confirm this result by calculating the larger volume calculation with these Bell parameters, and we obtain XZ equals 6.29, XF equals 6.1, and the n pi square is 0.00517, which is consistent with our target value. Okay, so let me briefly show you our result. So we use 2 different ensembles. we have a bunch of ensembles on these two different lattices, and tau times 6 times 16 cubic and tau times 16 cubic times 24. And as usual, we use anti-periodic boundary condition for temporal fermion, and for others we use periodic boundary condition. Then what do we expect from this finite volume finite temperature calculation? First of all, we expect that there is a deconfined transition by increasing temperature or decreasing the n tau. So, and the other expectation is that above the critical temperature, if the symmetry, so the global symmetry, the higher symmetry or unit symmetry is restored, we expect the parity partners in vector channel and pseudo-scalar meson channels degenerate. So, for example, there is a nice poster by Bastian about the two-flavor QCD SU3 theory, and yeah. Okay, so we determine this the critical temperature by looking at the Polyakov loop. So Polyakov loop receives the multiplicative renormalization. So by imposing the condition where renormalized the Polyakov loop for given reference temperature to be constant. So for this calculation, we use these three different reference points, and basically we look at the peak of the susceptibility of Polyakov loop and calculating, assuming the error from these different renormalization conditions. And we found that the n-tau critical equals 39.5, or the TC equals 0.0254 in lattice unit. Okay, so let me show you the temporal correlators. So this is a result of n-tau Fourier, which is below the critical temperature. So the basic feature of these temporal correlators are same as the zero temperature, where the pion mass decays very slowly, then vector meson and actual vector meson and scalar meson decay quickly. Then as you increase the temperature or decrease the n-tau, and n-tau equals 40, this is the onset of the critical temperature, basically. And we found that the vector meson and actual vector meson are degenerate. So this is the evidence of the degeneracy, the higher symmetric restoration. And maybe, yeah, thank you. So around the critical temperature or above the critical temperature, we cannot measure the mass from the temporal correlator, because no longer there is a simple pole in the structure. So, but we can still calculate the screening mass, where looking at the spatial correlators, and we can extract the mass from the correlators. Okay, so this is a result for axial vector meson and vector meson. So, and the axial vector meson slightly decrease below the critical temperature, and above the critical temperature, axial vector meson and vector meson are linear in T. So we take the ratio to see whether they are degenerate or not. So actually we found that they are not degenerate, so we expect there are some systematic errors going on. But still, even if there are systematic errors, we found a good signal of the degeneracy between these two mesons, where the ratios are very small, which the mass ratio is given by this, and the ratios are very small and flat. Okay. But we found that the above about 2 TC, the mass, the screen mass by the temperature is deviated from the plateau. So this is due to the lattice artifact for small n tau, because the lattice spacing is proportional 1 over n tau. And for the scalar channel, we have similar result, but the degeneracy appears about 1.5 TC. Okay, so one interesting thing is that the above 2TC. So we found that there is a lattice artifact is going on, but also we check with the isotropic lattice calculation, and below 2TC, this red and black and these green lines avoid each other. Green is for isotropic lattice, but above 2TC, there is this discrepancy between anisotropic lattice and isotropic lattice. This can be also understood as the lattice artifact. But if I rescale, so for this calculation, I use the renormalized anisotropic vectors. But if I choose the bare anisotropic vectors, then above 2TC, the isotropic lattice and anisotropic lattice avoid each other. So in this reason, we lose the information non-perturbative information of this calculation. Okay, so this is the conclusion. I think I don't have much time.
Okay, thank you. And questions, comments?
Just a trivial comment. You were emphasizing that certain boundary conditions were periodic and some were anti-periodic. In the case of an SU2 gauge theory, those two are identical. That's because -1 is an element of SU2, and so it can be absorbed into the gauge field.
Thank you.
Other comments? I need a comment on the tuning of the anisotropy coefficients alpha way before. Go back a few. When you measure the correlators, the Wilson loop, non-planar Wilson loop.
Okay.
So if you mix different orientation, basically, aren't you exposing yourself to the risk of different cutoff effects, and so you're measuring eventually something which is not very well defined?
Yeah, so actually,
cutoff effects will depend on the orientation with the lattice. If you stay on a single direction.
So actually, for this calculation, for non-planar Wilson loop, I pick the G and changing X. So from this minimization, in this ratio, so R plus 1 is not G for both G and X direction. Just I choose one of the direction. So this is similar to the planar case, but just extend the one lattice or one lattice or two lattice in J direction, and just I add more data points.
Yeah, but they are on different scaling trajectory to the continuum.
Shouldn't they be the same? I mean, if you stick to only planar, you say, look, I have no lattice artifact. But you're fooling yourself, because if you were looking diagonal, you would see a difference that vanishes like a squared. So it's not fair to say there was no artifact in the planar one, and the artifact was only, there were artifact in both, you just didn't notice because you were not looking.
I just want to say, you took the anisotropy at 0 temperature, right?
Yes.
And you say at larger temperature you do not find.
Right.
And did you check maybe the harsh perturbative anisotropics?
No, I didn't check.
Because at 0 temperature they are very different from the non-perturbative one. But there will be a test that at large temperature the problem is perturbative.
Okay.
Okay. All paper of video file.
Okay, good. Thank you.
Other comments? If not, we can speak again, and we reconvene at 4.